After he said the integer thing, we kind of looked back at that. But I still am confused on it. But he's about to go. Here we go.
All right. I think I am finally ready to get started here. Here's the your last chance to sign the attendance sheet. Very exciting. Maybe I'll top hat. Let's see here.
I think every time he's done top hat, I just haven't done it. I have like 2 out of 7 top hats inside.
Yeah, I mean, it's not like attendance matters.
Let's see here. Here.
Oh yeah, it's.
I keep forgetting to take the top out when I'm in class, and then like sometimes and then
Does he just not?
All right, here we go. Very exciting.
he forgets to write down the book.
Very exciting. Here it is.
Oh my goodness.
I remember that year. That was a good year. That was a good year.
All right. So I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for these students in this class, and just pray you'd help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right. So yeah, I did grade the computer projects. So my grading isn't terribly nuanced at the moment because too much is given, much is required. I didn't give you guys much. So, like for example, I think for project B, I wanted you guys to find inverse matrices. What I'm looking for there to make that interesting is like what I wanted, and I forgot to say this, is I want matrices full of integers. I want invertible matrices full of integers. So like some of you, like one of your groups just took like random matrices and divided by the determinant to get determinant 1 matrix. Very appropriate to my instructions, incredibly lazy, but also a very nice solution, nevertheless useless to my deeper purpose, which was to try to get you guys to give me a list of nice invertible matrices with integer entries, which I don't have to invent. Now the other group did like one step and gave me like an example, which is really a little bit, I don't know, I'd like to see more. Anyway, in a nutshell, I think the thing that probably did most violence to the assignment was the orth function, because basically the orth doesn't Gram-Schmidt in a nutshell. So when we try to use orth to Gram-Schmidt, it doesn't quite do it. Now, what it does do is it finds you an orthonormal basis for the set that you're considering. That is true, but it doesn't Gram-Schmidt. So anyway, I didn't take points off for that, obviously, because I encourage you guys to use orth and stuff. So that said, I think most people have missed points because you got to like something didn't check out. Well, if it didn't check out, that means you're just not done. Like all of these things check out. Every single thing I said to verify can be verified and was verified by some group, but just not your group. But anyway, people learned about MATLAB, and I think we achieved our purpose. So let's see here. Are we done? We're done with this, right? Yeah, let's get this out of here. All right, so test 3. Let's look there. So let's see here. Problem 1. Probably you guys don't have questions about problem 1. So to find the perp, I just put the defining vectors and calculate the null space of the transpose. That gives me vectors which are perpendicular to the given pair of vectors. But then, of course, the annoying thing is that they're not orthonormal. So run Gram-Schmidt on those. And when I do that, actually, did I even ask to find an orthonormal? I did ask to find an orthonormal base. Okay. Anyway, so I got that for my orthonormal basis, which gave me the closest point of 1 minus 1, 0, 1, which I felt good about because it happened to pop up in the solution set, for the null space. But anyway, so there's that. That's not up for grabs. Like that's the answer. Like there's not 2 answers there. That has to be the answer. Now, is it possible you're right and you found a different orthonormal basis? Absolutely, that's possible. And so I must be careful when I grade to not, if you have found a different orthonormal basis, you still have full credit, but you also still should have found that same answer there. Now, problem 2, I laid a trap for you guys, which is that the set which is given is not linearly independent, so we can't really run Gram-Schmidt on it. So we have to toss out the third vector or something like that. And so once I do that, then I have a linearly independent set. I can run Gram-Schmidt on that. And I'm sure this isn't my first try. My Gram-Schmidt's always wrong the first time. Which you should always check your answer when you're orthonormalizing, right? It's not hard to check the answer. Check for pairwise perpendicularity, basically. And then, so I get that. And then for W perp, I find the null space of the transpose of the vectors which define W, which ends up giving me this thing. And then, let me not talk so much because we've got a lot to cover today. So I got that, which gave me this mess. So I ended up with that for my answer. And pretty sure it's right. But I'll be more sure when I check your test 3 and I get 5 other people with the same answer. If I'm the only one with that answer and 5 of you have the same different answer, well, that means one of 2 things. Either I'm wrong and you're right, or I'm right and you guys all work together, but without thinking. So, but probably that didn't happen. A way to check on this would have been to calculate the projection onto W perp and then see that the sum of those 2 added to A, B, C, D. We could have checked it that way. I ran out of time, so I don't have the check here, but let's see here. Problem 3, the matrix 1, 3, 3, 9. The characteristic equation here is easy to calculate. So it's going to give you a 0 and a 10 for eigenvalues. And then I just worked out the eigenvectors. Now these eigenvectors you probably get, so for a 2 by 2 matrix, I find that often for a 2 by 2 matrix, I can guess eigenvectors. And so if you have that insight and you can just write them down, by all means do so. Otherwise, write down the 2 equations, 2 unknowns, and work it out. Of course, if you did it right, they should always be what? For the two-dimensional eigenvector problem, you should always have the one equation and the other equation are just linear multiples of each other, right? So you don't really need to do row reduction. You should check on it, make sure you're not, tricking yourself. Because if you've got genuinely different equations here, you've done something wrong. You need to go back, figure out what you did wrong. Probably your eigenvalue is not really an eigenvalue in all likelihood. But also, popular mistake is just to not set up this matrix right. That's not hard to do. Or write nonsense like matrix equals column vector. What's that about? So yeah, don't do that. Goodness gracious, -5, -5. At least I should elevate these to imply symbols or something, because they're definitely not equalities. See, I'm going to have to go fix that after class before I post this thing. All right, otherwise it'll bother me. Anyway, so I got my orthonormal eigenbasis there, as is my right, since it's a symmetric matrix by our choosing. And then I solve for x in terms of y. So if y is equal to beta inverse x, but here beta is beta transpose because it's orthonormal, right? Then I can solve for x by multiplying by beta. And I get these coordinate change formulas. Here's x's in terms of the y's. In other words, x is in terms of the eigencoordinates. And I just noticed a pattern here. So why not, So it's x plus 3x2 squared. So that makes it easier because I just have to put in my x1 and my x2. Notice that they be canceling like here and here. And then 1 plus 9 is 10. And then 10 over 10 is 10. Now this is non-negotiable. You should expect this answer here. Everybody should have got this answer because we should all understand the following theoretical calculation, that if we have a quadratic form and we rewrite it in terms of eigencoordinates, what happens is we get, y transpose dy, where d is the diagonalization of the matrix. So we get an eigenvalue weighted sum of squares of the eigencoordinates. You could write that formula down without so much as calculating the eigenbasis, right? Sometimes I ask a question like that on an exam where I say, just write the formula down. You don't actually have to find the eigencoordinates. All right, this one here, as I tried to warn you guys in the hint, is easier than some of you were making it because I've already given you the power series expansion, so I just, excuse me, write down the matrix of the quadratic form, calculate its characteristic equation. If you use technology, totally fine, but I would point out that this is an example of a 3x3 matrix that we could figure out by hand reasonably on a test, for sure. This one is pretty sparse, like you guys should be able to hack your way through that. Anyway, we get eigenvalue -2 repeated and eigenvalue 4 the other thing. So this is the formula. See, this is the formula for the quadratic forming at eigencoordinates. I'm using my remark right here, right? I didn't actually calculate the eigenbasis. I just know by the general result that the formula can be written in terms of eigenvalues and eigencoordinates like such. And as such, it's increasing one direction and it's decreasing other directions at the critical point, which means we don't have a max or a min. We've got a saddle. So f of 42 is neither a max nor min. Now, about the time of night I was doing this one, I forget what happened. I think they were playing Halo. I don't know. It was loud. And I started doing something really stupid. I started trying to find the SVD for this. So like, just point of order on the final, make sure you're doing the right thing, right? Like, don't be finding the singular value decomposition where I've asked you to find like the LU decomposition or something silly like that, right? Like, do the problem that you're asked, not the problem that you invent, like me here. I haven't shown you the work, but it's not fun to try to find the SVD for this one. It's like, I mean, it's not impossible, but it's not as much fun as this. So here we're working trying to find the QR decomposition. Like I said, I didn't do the Gram-Schmidt by hand here. I used, man, what did I do? I used Wolfram Alpha. Wolfram Alpha actually does Gram-Schmidt, I believe, much better than, say, Orth. I don't know what would happen if I'd done Orth there. And that matters here. Obviously, this won't matter in the final because you're not allowed to use your computer on the final, right? But for future reference purposes, if you're trying to Gram-Schmidt, you can't use Orth because, well, it depends on your purpose. If your purpose is just to create a projection map, using Orth would be fine. But if your purpose is to find the QR decomposition, Orth is not a good fit because it scrambles things. It doesn't put them in the same order, and the ordering matters for the QR decomposition. All of that said, I'm pretty sure there are built-in MATLAB commands for like the QR decomposition, for the singular for the SVD, for any of these standard matrix factorizations. There's certainly a built-in MATLAB command, and that's what you should be using past this course, right? We're just using computers in here to try to not make some of these larger problems so onerous. Anyway, so that gives me my Q. And how do we find R? Once you got your Q, so like, to rehash, what's the QR decomposition algorithm? It's pretty simple, right? We take the columns of our matrix. We have to, for this to be a reasonable question, what do you need to know about the columns of your matrix? If somebody asks you to find the QR decomposition, what is presupposed about the matrix? Like, I couldn't take the vectors that define W in problem 2 and concatenate them into A and say find the QR decomposition. Why? They're linearly dependent is the answer, yes. So we need linearly independent columns. If you have that, you can Gram-Schmidt the columns. That gives you a set of orthonormal vectors, which you glue those together. That gives you Q. And then to find R, well, just think about what you're trying to do. You're trying to find A is equal to QR. If you multiply that both sides by Q transpose, because Q transpose Q is I because they're orthonormal, we're able to find R by Q transpose A, which is what I do here. And voila. So there it is. Also, let it be understood that like if I was to ask a decomposition problem it is perfectly acceptable. Like, I wouldn't take points off if, for instance, I had factored a half out of this, you know, and I put like a half over here. As long as I'm clear that the half goes with the Q and not with the R, like, I wouldn't take points off. That'd be fine. We don't have to put all the numbers in the matrix if it's not, you know, it may be convenient to like leave a fraction out or something in certain problems. All I'm saying. Anyway, an important thing you should know about is that if we have a QR decomposition, it's super nice for solving the corresponding least squares problem. See, because if we look at that, put in the QR decomposition for the normal equations, we get this, which implies that the normal equations are equivalent to Rx equals to Q transpose B, but that's a upper triangular coefficient matrix R and Q transpose B. Well, that's just a thing, whatever it is, and so we can just straight solve it. So here it is, Q transpose B gives me this, and so then I can just solve these equations by just straight back substitution, like working my way up. I got 2z equals minus a half, z is minus a quarter, shove that in here, get y equals 2, shove that in there, gets x equals minus 21 over 4. Oy. So I get the approximate solution of minus 21/4, 2 minus 1/4, and I said, well, I better check it. So what I did, since I have a computer handy and all this stuff, I multiplied A transpose by A, I multiplied A transpose by B. That gave me so here's the augmented coefficient matrix for the normal system, for the so-called normal equations to the least squares problem. And lo and behold, same answer. So yay, which I hope is the same answer you guys got. Because if you guys got different answers, then I have to figure out how many points to take off, and that's annoying. It would be much, much simpler for my grading if everyone had the same answer and I could just give everyone 100. That would be wonderful. Wait a minute, how much is the test worth? Let's 150. I hope everyone gets 150. That'd be better. But some of you like refuse to do like bonus. You're like 140 is all I need. The other 10 points are bonus. I don't want those. Other people might hear I got bonus points and they'll think I'm a nerd. I'm not sure exactly what the calculation is, but some people give up once they realize they're in bonus territory. Which is why I've generally tried to be much more vague about what's my bonus question. I used to like clearly demark them as this is bonus, but then I'd found out that like 30% of the students just don't even bother. So I no longer mark them as bonus. Because I don't want anybody to give up on themselves before they try. Yeah.
Is there a certain question on this test that was in your head that was bonus? Or?
Not really, no. I mean, I think we'll know it when we get to it. Yeah. This is a final exam question often. Because this is not a hard question, right? If you've done your homework, not this literally, you know, but the idea of it, find the best fit line. So what do? You write down the equation of a line, you plug in the data, it gives you an inconsistent system of equations, which then you can solve the best approximation to the solution by solving the normal equations, right? Or I guess if you really are a glutton for punishment, you could find the basis, an orthonormal basis for the column space of M and calculate the projection onto M using the orthonormal basis and then solve the projection of, you know, the projection equation of the given equation. But no, don't do that. Solve the normal equations, be normal. Should we call them cis equations? Let's see here. Oh, I'm sorry, too soon. But it goes with the mug. Let's see here. So this is a gift from my mother before you think bad of me. And my bigger mug, it broke. I dropped it on the ground. It's sad. And my son put it back together with tape, but I'm not going to try to put coffee in it. Anyway, yeah, so that's what that gets to. Yeah. So notice here that every step of the way, things you got to be able to do by hand, like multiply matrices, get you a 2x2 matrix, invert a 2x2 matrix, you know, not to mention the general construction of the least squares problem is something you should have clear in your mind for the final, right? You shouldn't have to spend a long time. You also have a sheet of notes, right? Yeah, so it feels like something that ought to be on there And you're allowed to put a sentence there that reminds you how it works if you want. That's fine. Let's see here. This one, what was this one? Oh, I've forgotten what the problem was. One moment. Oh yeah, it's supposed to diagonalize the matrix and then calculate e to the ta. So this one is, so like the start of the problem, part A, test appropriate, for sure. Diagonalize the 3 by 3 matrix with integer eigenvalues. We can do that all day long, not a big deal. It would take us 15 minutes of our test time, but it's something we could do, you know? You ought to be able to find the eigenvalues of 4, 7, and 12. It would take a minute to work that out without technology, but you ought to be able to do it. I mean, I might need to give you a push in the right direction here because perhaps it's not obvious to how to factor the cubic polynomial that results from the characteristic equation here. So if this problem came on a final, it probably would come packaged with a hint like either, hey, 4 is an eigenvalue, or as I'm more likely to do, hey, by the way, you know, if you look at the vector minus 1, 0, 1 and you multiply by a, you get, you know, like 4 times minus 1, 0, 1. That's interesting. So that's probably how it would come to you, which you'd have to process that information and go, oh, lambda equals to 4 is an eigenvalue, which means I can factor lambda minus 4 out of the cubic polynomial, which is the characteristic equation here. You know, so I do give information in that kind of circuitous fashion sometimes. So you need to know what an eigenvector is, what an eigenvalue is, the relation between eigenvector, eigenvalue, and characteristic equation. Anyway, I could spot from just looking at the website that U1 was that, but when I looked at the U2 and the U3, I couldn't really see from the decimal what the exact form was, and I wanted the exact form. So what I did was I went back and I just looked at a minus 7i, which gave me this, you know, which can reduce to that exactly, which gave me that exact. Oh, and I haven't fixed it yet. You guys are not wrong. I am wrong. I know you guys are thinking about this right now. What is it supposed to be? What? Negative 132. Is that wrong? Negative 132? No, it's worse. 14. Yes. If you add 1 squared plus 3 squared plus 2 squared, you do not get 15. And so that is, yeah. So there's going to be a lot of those mistakes coming forward. So I thought the 46 should be a 45. I'm like, nah, that doesn't right. No, it's not the 46 that's the problem. It's the 15s, of which they are legion. So this isn't quite right at the moment. I need to fix it. The spirit of it is right. All right. So listen, you guys, if you use the MATLAB command to calculate the matrix exponential, that's fine as long as you did it correctly. So I won't mind if you use the MATLAB command to calculate the matrix exponential and you didn't actually calculate the matrix exponential, well, then that's unfortunate, but I will have to take out points. On the other hand, it's ugly. So what I did was to notice that, excuse me, p, a to the power n is, you know, p d to the n, p to the minus 1. Actually, that's not what I did. To start with, I assumed that p transpose was p inverse, which is incorrect because this matrix is not symmetric, which is a trap that I laid for myself. And as such, well, you can see. So, but there's some lessons to be learned here, so let's talk about my errors. First of all, I have carelessly not normalized to 14 as I should have, right? So that's a problem. But there's a deeper problem here. I've assumed that p inverse is p transpose. That just ain't the case. The reason for that, in part, is because A was not symmetric. So the eigenbasis didn't have to be orthonormal in this context. And in fact, it wasn't. Which means, in this context, I actually have to straight calculate p inverse. I can't just transpose it. You know? And so I got down to all this. I did all of this, right? And I'm looking at this. I'm like, it's not. And I thought, well, how can I check my answer? Well, we know something about the matrix exponential. What is e to the 0? It's 1. And by 1, you mean the matrix, the 3 by 3 matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So if I did my work correctly, I ought to be able to put t equal to 0 into this and get 1, 0, 0, 0, 1, 0, 0, 0, 1. You can try. It ain't the case. So I knew I was wrong. I'm like, where is it? I thought the normalization factors, and then finally dawned on me, you idiot. A is not symmetric. I can't be assured that there is an orthonormal eigenbasis. The thing is, you're like, can't you just take the eigenbasis and Gram-Schmidt it? Well, sure you can, but when the process of Gram-Schmitting, you're not necessarily getting an eigenvalue. I mean, eigenvector out of the Gram-Schmidt process, you see? So only for like a symmetric matrix is it possible to be assured that like the Gram-Schmidt process will produce eigenvectors. Okay, so now that I saw that, I was like, well, if I'm not using an orthonormal p, I might as well give up on the stupid fractions anyway and use an integer p since I'm inverting this thing anyway. So I went with that, and then I inverted it. I got that. I went back to my standard trick. If I'm going to calculate the matrix exponential by hand, there are 2 ways to do it, basically. Maybe 3. The one is to just straight calculate it. You had some problems like that, right? We'll get to those in a second. If you just can calculate the power of the matrix explicitly, when you can just calculate it out, right? Do the power series. The other thing is, if you have if you have a Jordan basis, then you can actually calculate this somewhat concretely. You don't. There's yet another result here, which is that. I mean, this isn't wrong, but this is in the diagonal case. Like more generally, if you have the Jordan form, the way it works is e to the ta is equal to like the basis matrix inverse e to the t, the Jordan form of a, times beta. So like if beta was the Jordan basis, then you can do that as well. And it still works if it's a real Jordan form with the understanding that you have to put real Jordan blocks as appropriate up there. And this e to the ta is pretty simple to calculate. We had some problems in the homework where we did that, where we actually had like lambda plus n, and we saw how we can actually calculate that. So that's like not as bad as it looks. Anyway, so after I adjusted and accepted the humiliation of my previous attempt and gave up on it and switched over here to p and p inverse, I got this beautiful formula. And to answer your question, maybe this is the bonus. I don't know, it's ugly, but it's a take home, so whatever. Anyway, so 15 plus 6 is 21, 21 plus 9 is 30. This also works out to 30, this also works out to 30. So 30 over 30, 30 over 30, 30 over 30, these are all 1, and everywhere else you can check at 0. So it's I'm either right or fantastically lucky to have it work out to e to the 0 as 1. All right, enough of this. Let's move on. This one here, the characteristic equation here is not too bad. It works out to lambda squared plus 1 squared. The one eigenvalue is easy to find with technology. The other one I had to work out like this. Anyway, I got this as my real Jordan basis. So by real Jordan basis, guys, what I mean is I take the real and imaginary parts. So like v1's an eigenvector with eigenvalue I. This is the real part, this is the imaginary part. v2 is a generalized eigenvector of order 2 that solves a minus ii a minus ii times v2 equal to v1, and the real part and the imaginary part of v2 are here and here. So when you string out the real and imaginary part of a complex generalized k-chain, it gives you what's called the real Jordan basis. And then now you didn't have to do all this. Like you could have just quoted the result from my notes. That would have been totally legit. I'm just including the calculation here to emphasize how it's done, which is just to multiply out and keep real and imaginary parts of both sides. And as such, this is the general solution. So you take C1 times the first, C2 times the second, C3 times the third, C4 times the fourth. And if you look at the first one, that basically comports with what we do in Math 334, although it's a little bit uglified in the sense that, like in 334, we would tend to write like cosine, sine, t cosine, t sine for our standard solution in the case of a repeated complex eigenvalue. I guess we call them eigenvalues, don't you? Or you call them characteristic value. What do you call them? Characteristic value. So some books call them eigenvalues because they are. But anyway, fun fact, for those of you who have the differential equations cheat code to this course, whenever you do this, whenever you find the corresponding coefficient matrix for doing reduction of order for a system of, for a differential equation, the characteristic equation of that matrix will always be the same as the characteristic equation of your original differential equation. It's not an accident that if you look at the first equation there, you get lambda to the fourth plus 2 lambda squared plus 1 equal to 0 for you differential equations people. That's exactly what we have down here. That's not an accident. It has to happen. If you do reduction of order on like two systems which are decoupled, you'll get a product of the characteristic equations which you're decoupling. Anyway. Oh man, I didn't talk about decoupling this semester. Dang it. Oh well. Where could I talk about decoupling? The final. Sam knows. Sam understands where I was going with this. But no, I'll behave. I probably won't teach you anything on the final. When's your final? Thursday? Oh, see, that's not enough time for me to plot against you. You should be safe. I'll probably have to recycle ideas I've already have, so you should be fine. You're given vectors v1, v2, v3, v4, v5, and the question is what to do with them. So I just work out the given data. There's my formulas, and I'm asked to find t beta beta. This is something you ought to be able to do. We have a definition for this, the matrix of t with respect to a basis. So all I have to do is calculate, t of this, t of that, t of that, t of that, find its coordinates. So you should be able to find the coordinates of a vector with a basis, like this. That is one of the theoretical things I do want you to be able to do. And so doing that, it gives us this matrix, which, in terms of the nomenclature that I introduced, it's the 2 by 2 real Jordan block with complex eigenvalue 3 plus 2i. That's this piece, and this is the 3 Jordan block with eigenvalue 4, just like that. All right, moving on here. Oh, this one was fun. Yeah, if you just, basically here's a game you can play. If you have a sum over all integers, you can always break it up into you can partition the sum into disjoint classes. In this case, like 3k plus 3k, 3k plus 1, 3k plus 2. These are, three cases. The union of those three cases gives us the totality of all positive integers, non-negative integers rather. And so I can break the sum over n to a sum over k threefold like so, and then simplify, and there you go. So, yep. I could say more about this, but I will not. So at this point, it was pretty late, and I was tired. So in the best of all possible worlds, I would suffer back through the lecture examples yet again, but I'm lazy, so I did not, because this is the book example times 2, right? That's the book example we worked out in class. Multiply by 2 gets you this. So if you think about taking an SVD, which you already have, if you multiply by 2, you can leave u and v alone. You just multiply the middle, the sigma, by 2, and that's still a orthogonal with a appropriately diagonal middle term. So there you go. That one. That's your singular value decomposition. And this one likewise, multiply the middle by 2. I didn't even write it out. See, I'm even getting even lazier for this problem. But if you could use your imagination, u is the same, v is the same, this is twice that. So you should have 6 root 2, 0, 0, 0, 0. Of course, if you didn't rewrite it, I think I had left it as a square root of 18 in class. If you wrote it in terms of that, I should not take off points, unless you didn't put 2 times square root of 18, because that's what you should have here. Okay, enough. So, might I ask a singular value decomposition on the final? It's possible, right? Would I ask this one? No. I would definitely not do that because, yeah. So, all right. So first of all, EIG is not helpful because EIG puts things in, it makes the spectrum increasing. So the spectrum is the set of eigenvalues, right? So this goes from like eigenvalue 0 up to like eigenvalue 20 or something, which is the opposite of the order that you want for what we're doing. So that was like, I mean, it is what I enumerated them in my handwriting here. So as you can see, like the eigenvalues, they're not quite what I want. But then I checked AP, and I got the 0 for AV4, which is what I want. And then those other 3 vectors, well, they're not normal yet, but you normalize them. Well, that's the thing is I tried to use orth. This was the point at which I realized orth is not my friend. See, because it's just not, well, anyway. Maybe it's, I don't know. So I at this point I was like, well, I don't trust the orth. So I'm going to use the SVD in MATLAB instead, which maybe you did. And that's okay if you did. It's not really what it is. Well, anyway, let me shut up. So the sigma part, which they use S for, because why not, is that. Here's the U, here's the V. And if you go back, you can check, you can actually see that I was getting, I had got this correctly on the previous page, but I don't think my U matches what orth did, if I remember right. I don't think it quite matched. Maybe it did, I don't know. Did my U match the orth? Ooh, what the what? For example, like, if you guys can remember 2171, 3455, and 8451. 21. I don't think it quite matches. Yeah, I think it's, well, anyway, this nevertheless is a correct SVD here, and as such, I can peel off the. Why is it yellow? What's going on here? Stop that. I can peel off the R part of it. Which R is 3 here, so I peel off the U3 and the V3. That's a formula for A. D is just the diagonal part. The non-zero part is S. And so there's the pseudo inverse, which is this, which thanks to, I think Sam suggested there was a website. I was like, oh. And I found that website as well. And I found this answer on the website, which makes me feel good. So anyway, there's that. Obviously, so like to find the Moore-Penrose inverse, I don't think that's a likely test question. It's just too much inside baseball, and like it's just too much. Now I might have there are good theoretical questions to ask about like any of the decompositions, because so like if I want to ask you guys a symbolic matrix calculation, like solve for the matrix in some way or another, where you don't actually have matrices, you just have like a formula for matrices. These factorization schemes make nice questions about that, right? Like, for instance, given the factorization scheme for A, find the factorization scheme for A squared. That could be a simple just matrix algebra problem that you guys should be able to solve using things like properties of inverse, properties of transpose, that sort of thing, But anyway. This here, I think I did too much in lecture. I made it uninteresting. I'm sorry, guys. I did way too much in lecture. I should have like left this for you to discover to make it more exciting. But yeah, it's the sum of squares, which means, like I said, you could use that to find the inverse of a quaternion. Every non-zero quaternion has a multiplicative inverse as it happens. And by the way, eta eta star is the same as eta star eta, which is not immediately given to us because they don't commute. But it is true that either direction actually gives us the sum of the squares. Fun fact, you can work out formulas for like, well, this is true. ZW star is equal to W star Z star. So like this is the formula. So when you conjugate a quaternion, it flips the order around like this. But if you look at ZW squared, you'd have, well, ZW star ZW, which of course would be, it would be W star Z star ZW, which would end up being the length of W squared times the length of Z squared. So that actually gives you a formula. So think about this in your mind for a second here. I mean, I don't know where else you're going to think, but Z times W is a product where you have these like 4 terms: the real part, the imaginary part, the imaginary part, the imaginary part, right? Those are all built through this somewhat complicated way of multiplying the quaternions together. On the other hand, you have W squared and Z squared. That's a product of the sums of the squares of the numbers. So this formula actually gives you a relation between like a sum of 4 squares. It's a 4-square identity. And that allows you to do weird number theory stuff, actually. There's a similar formula for complex numbers, which basically is really integral to a large chunk of algebraic number theory. If you've had that course with Dr. Schmidt, you might know what I'm talking about. I don't know. But there's a similar thing for quaternions, but that's it. There's no like 8-square identity. There's just this. There's a 2-square identity, a 4-square identity, but I think that's it. But anyway, so I'm sorry, I don't seem to have gotten back to test 1 and 2. I mean, here they are. Well, test 2 was what? Determinants, eigenvectors, transformations. So those things should be on the final. I think the final would probably be something, if I had to guess, something like 40% test 1, 30% test 2, 30% test 3. Of test 3, the problems that are sort of more amenable for in-class testing probably are more with like the closest vector problems. Those are a little bit more, I think, intuitive. You know, find the orthonormal basis for the perp, that kind of thing. So, well, I don't think I'm going to say anything else useful in the time that remains. So, I mean, there's no time, right? So, I'll shut up. It's been a fun semester, guys. See you at the final.